All right, so this topic of electromagnetic radiation, which is a lot more intense, or sounds a lot more intense than it is one of the ways that energy travels through space. Okay? And most of the time, energy travels through space, okay, in a wave form. Okay, what's a wave look like? Make it with your hand. All right? Waves like that. Okay? Waves go up and down. They have really strong characteristics called peaks and troughs and wavelengths and frequency and all that kind of stuff. Okay, so we're going to use 3 characteristics to help us describe waves or how energy travels. And those 3 topics are called wavelength, frequency, and speed. Oh, my iPad is just having little problems here. Okay. Wavelength is the distance between 2 consecutive peaks or troughs on a wave. Okay, and I'm going to show you what a wave looks like here so we can point those out a little bit. Frequency is the number of waves per second that pass a given point. And then speed is the speed of light, 3 times 10 to the 8 meters per second. You'll need to have that down. And if you want to get an equation sheet for this chapter, you can. If you want to come grab a little colored piece of paper, or if you want to add to your old one with gas laws on there, you can do that too. But if you want to come grab a new one, they're up here right in the front. Okay, C equals, does anyone know what this symbol is called? It's a Greek letter. This one's called lambda. Lambda, okay? But really, we just think of it as wavelength. Okay, so it's speed of light equals wavelength times the frequency of the wave. Oh, sorry. I didn't know that it skipped forward. Okay. C is the speed of light measured in meters per second. Frequency is basically cycles or revolutions per second. And then wavelength is meters per cycle. Okay, so all of our units end up canceling out here. But I will tell you that wavelength needs to be measured, or it will be measured in meters. Okay, this is measured meters per second, and this is like waves per second, or cycles per second, or however you want to say that, that's fine. Speed is always given. The C, the speed of light, that's a constant. It's always 3 times 10 to the 8th. C is always 3 times 10 to the 8th. Okay, so the speed of light. So I'm going to show you what a wave looks like here so we can look at some of the attributes of a wave. Does everyone have what they need to on this one?
Wait, so the C1 is for speed?
Yeah, C is speed, and it's always going to equal 3.0 times 10 to the 8th. So you can put that on your equation sheet as a constant for C. Pictures. A wave has specific attributes, right? A peak is at the top. Okay, maybe if it'll look right. Here's a peak and a trough, or a valley, sometimes they're called, right, of a wave. So a wavelength has to be from identical points on the wave. So this is not a wavelength. Here to here, that's not a wavelength. It's got to go here, all the way to here. Right? That would be considered a wavelength. So they put wavelength of this wave. Here you've got a wavelength here. It's always peak to peak or trough to trough. That counts as one wavelength. Okay? Up here you see you have a little bit longer wave, so your wavelength is a little bit longer. So the more frequently that a wave waves, right, you've got a shorter wavelength and a higher frequency. So you'll notice that frequency and wavelength are inverse relationships. As wavelength gets longer, direct relationships, I'm sorry. As wavelength gets longer, frequency gets longer. All right. When we talk about energy in waves, it can only be gained or lost in whole number multiples of this equation or this term called HV. H is our something called Planck's constant, and it's given right down here. Planck's constant. Okay, so that needs to go on your equation sheet as well. Frequency, okay? So we're going to be able to look at the energy of a photon, or one of those light particles, right? That's what a photon is called. A light particle is called a photon. And so we're going to be able to look at the energy of the photon using this equation. Energy of the photon equals Planck's constant times its frequency. Okay, and here's Planck's constant right here. You can manipulate the equation to also equal Planck's constant times the speed of light over its wavelength. So you can put this whole equation or variations of this equation on your equation sheet. Okay, the energy of a light particle or a photon can be found by taking Planck's constant times its frequency. Or you can expand it out here. Sorry. V is frequency, E is energy of our photon. So your book goes on to explain a lot more detail that goes into energy of photons. But what it basically boils down to is that they used to think that energy was just this continuous stream, basically, of values of energy. But this guy called Planck, right, he discovered, discovered, that energy can only be found in whole number quantities, kind of, called these quantums. And so these whole number quantities, he developed this constant to take times its frequency to find the energy of that photon in particular. Okay? I'll read exactly what the book says, but there's a lot more detail that goes into it if you would like to read about it. It said, it had always been assumed that the energy of matter was continuous, which meant that the transfer of any quantity of energy was possible. Now it seemed clear that energy was in fact quantized and can only occur in discrete units of size hv. So there's our energy right there. Each of these small packets of energy is called a quantum. A system can transfer energy only in whole quanta. Thus, energy seems to have particular properties. Okay, so he discovered that rather than energy being this big stream, he said you can only give energy in these little pockets called quantums. Okay, again, that's probably more than we need to know right at this minute, but there is a reason behind all of these equations, basically. Okay? Moving on to the next guy that made a discovery, he attached mass with that. Okay, he attached mass with that. So I'm not even going to try to say his name because I don't know how to say it and I don't speak French, so I'm not going to. He attached mass. So you can put either of those variations of that equation in your equation sheet or on your equation sheet. Okay, he said the mass of the photon could also be used in our equation. Okay, by putting in mass, in wavelength, and frequency, we're now able to look at things that are not just photons. We can look at bigger objects that are moving or bouncing or moving in a wave-type pattern. So we're going to look at comparison of an electron and a bigger object here and look at what their energy levels are here in just a second. Okay? I know this seems like a lot, but we'll get through it. I would put that constant on your equation sheet. That's called Planck's constant. Times 10 to the negative 31st. Wavelength is what we're solving for. And V is, remember, frequency or speed. Okay, not speed of light. Speed of light is the little c. Speed of our object that's moving, it can be considered the same as frequency. It's how many cycles per second or meters per second or whatever. Okay, so our speed of our electron is 1 times 10 to the 7th. So if I wanted to solve for wavelength, I'd go back and look at my equation, and I know that wavelength equals h over mv, right? Is that the equation that you have down? Okay. One more time. Okay. Wavelength equals h over mv. I will tell you in your calculator, do we know how to store numbers in your calculator? Okay, if you have a calculator that has an STO button right down here on the bottom, right above on or off, STO with an arrow, what I would do is I hit in 6, I'd go ahead and plug in Planck's constant, 6.626 times 10 to the negative 34th. Is that Planck's constant?
Do we do like A?
Yeah, and then you go store, hit the store button, and then I stored it as alpha and then the letter H because Planck's constant is an H. So I went alpha H, and so that means anytime I need to use Planck's constant, I can just hit alpha H, and then it's already got that number plugged in, so I don't have to hit 6.626 times 10 to the negative 34th. Does that make sense? So I hit the number, 6.626, second E, negative 34, and then I hit the little store, STO arrow, and then I pick what I want to store it as. And for me, I wanted to store it as the H letter. So I went alpha H, which was at that caret button. Then I hit enter.
Is that what the purpose of all those letters are?
Mm-hmm. They give you places to store things. Okay. Okay, so now in my equation, when I want to solve that, I'll just do my alpha H divided by the mass, 9.11 times 10 to the negative 31st, divided by the speed. And I got a wavelength equal to 7.27 times 10 to the negative 11th.
Wait, what did you do?
I took the speed of, I took Planck's constant divided by mass divided by velocity. So if I write it out, it's Planck's constant over 9.11 times 10 to the negative 31st, 1.0 times 10 to the 7th, equals my wavelength. Right? H is my constant, so I know what that number is. I just don't want to write it out every time. Is that about what we had? 7 point. Give me like a head nod if that's what you got in your calculator. Or not so much if you didn't get that in your calculator. Okay. So, moving on to how electrons work within the atom. Okay? This guy called Niels Bohr, he came up with this idea about the electrons around the nucleus of an atom. Okay? And he said that electrons could only orbit in a certain path. They could only orbit in a certain circular path. They couldn't leave that path or be fit anywhere in between. Okay? He said that electrons are at their lowest energy when they're closest to the nucleus, which we still think is pretty true today. But his theory has been since proven incorrect. We just like to talk about it because of the new way of thinking, basically, he brought about. So what he said about electrons is that they only circle the nucleus in really strict circular paths. They're at their lowest energy when they're closest, and the energy levels are like rungs on a ladder. So you have to be on an energy level. You cannot be anywhere in between. Or you have to be on part of the ladder in order to stand on the ladder. You can't float anywhere in between. That's what he said about electrons and their energy levels. Bless you. So when Bohr was doing all of his research, he was researching hydrogen atoms. Which hydrogen atoms have how many electrons? Only one, right? And his process seemed to work. And so he did all this research, and he did all these good things. But then when we tested them on other elements, it was no good. So his model really only worked for hydrogen, because we know hydrogen has one electron in a circular orbital called the 1s orbital. Okay, and that's what we're going to get into today. Okay, but his model basically only worked for hydrogen atoms. So he did a lot of work, but no go. Okay. So now we're going to get into what I would like to be the main kind of focus for today. I know we spent a lot of time on wavelength calculations, but that's not going to be the main focus of our chapter. The main focus of our chapter is something called electron configurations. And so we're going to talk about how electrons are configured within an atom, where they're located in an atom, all that kind of stuff. Okay? So, electron configurations is the arrangement of electrons within an atom. It's how they're arranged. If we were going to try to locate an electron within a particular atom, we would use its electron configuration. Okay, you don't need to put all the extra stuff here, but we're going to look at something first called ground state electron configuration. And that's when elements and atoms and electrons, they're all at their lowest possible energy states. Right? They're relaxed, they're fine. They're not what we call excited state electrons. The ground state electron configurations is when we have just neutral atoms that are just hanging out. Okay, and so that's what we're going to look at first. The arrangement of atoms in the arrangement of electron within an atom that's relaxed. Okay, those are called ground state electron configurations. That's when an atom is in its most stable condition, is when it's ground state. Okay, if you have your periodic table with you, I'd like you to get that out now. We're going to label some things on our periodic table.
Did you say it's in ground state, so lowest possible?
That's right, lowest possible energy level. It's its most stable there. Okay, so when we're looking at electron configurations happen to mimic the periodic table really well. We see trends for electron configurations on the periodic table really, really well. And so on your periodic table, I want you to label for right now, the S block is these two columns here, these two groups, the S block. P block are these 6 groups on this side. D block are the transition metals here in the middle. And then the F block happen to fall into the lanthanide and actinide series. Okay, so it's okay that you don't quite understand what I'm talking about yet. I'm going to label them, and then we're going to walk through how we get to that point. Okay, so S block is the first 2 groups. P block, these groups over here, D and F. Okay, so just label them for now, and then we'll get to talking about really what that means. S, P, D, and F. And it doesn't, the labeling of the blocks doesn't actually have a lot to do with the periodic table itself. It just happens to be that the periodic table mimics the patterns that we see in those elements. So we use it as a tool for us to find an element's electron configuration. Okay, do we all have it labeled? You don't have to shade them in or anything, just kind of get them labeled so you know where they're at. Okay? Something else that maybe you want to do, maybe you don't, I don't really care, but you can label periods. So 1, 2, 3, 4, 5, 6, 7. There are 7 periods to the periodic table. Okay, you'll notice that as we go down, it's 1s, 2s, 3s, 4s. But the d orbitals, you'll notice, even though they're in the 4th row on the periodic table, their block number is shifted up 1. Okay, so even though it's in the 4th row, right, this first energy level is in the 1st row, second energy level is in the 2nd row, third energy level is in the 3rd row, right? As we move down on the periodic table, those atoms, they gain an energy level. So they gain another shell of electrons. That's what's happening. And so these d orbitals, although they fit in the 4th row, really they're found in the 3rd energy level. So that's the only kind of glitch here. The same thing happens with the f orbitals, except they're shifted up really 2 rows, right? They're found in the 6th, right? If we put the lanthanides right here, they'd be in the 6th, but really they're in the 4f and the 5f block. So you can label those if you want. You really don't need to. The only thing I think you really would want to note is that you have a 3d orbital first and a 4f orbital first, okay? So if I were to ask you what block is sulfur in, what would you tell me? Find sulfur in your periodic table, tell me it's a 2s or it's a 4p or it's a whatever. It's in the 3p block. So it's in its 3rd, it has electrons in the 3rd energy level and in a p orbital. That's what that kind of is telling us. Does that kind of make sense? It's outer electron. It's in the 3rd energy level and it's in a p orbital. And so we're going to break down even further what that stuff means, but I want you to be familiar with how the periodic table is laid out in terms of its orbitals. Okay? Here we go. I'm going to give you this handout to help us determine what order do electrons get added. What order electrons get added in. Okay, so I know we'll have to get these handed out to other people, but you can keep this. You'll get to use this little pathway, I call it, on your tests and stuff. This helps us to determine the order in which our electrons are added to an atom. If you got extras, just put them on an empty table and I'll come grab them here in a little bit. So look at your periodic table and look at the pathway together. 1s is here. 1s, and really helium should really fit over here in this block nicely, but you know, the periodic table is not perfect. So when we put electrons in, we fill the first energy level first, the 1s orbital. And then once that's full, we move down and we fill the 2s orbitals. And then we move and we fill the 2p orbitals. Right? So are you following along on your pathway? Can you see how that works on your pathway? Take your finger and follow that arrow. We fill the 1s orbitals. Then we go down and we fill the 2s orbitals, then the 2p orbitals. Then we add another shell of electrons and we add 3s orbitals and 3p orbitals. Then we add another shell and we fill the 4s, then the 3d, then the 4p. Do you see the pathway, how that follows along? So when you're adding electrons to an atom, you have to follow that order. You fill an orbital, and then you move to the next one. And then you fill that, and if that's full, you add another shell, and then blah, blah, blah. That kind of makes sense? Okay. When I say orbital, do you guys know what I mean when I say that? I haven't explained that a whole lot, I guess. An orbital is like an electron pocket. It's like a holder for electrons. It's where they live, right? It's where they are, like that's their space. Okay, so an orbital is an electron holder or an electron pocket. Why don't you I want you to go ahead and write down too that an electron orbital can hold 2 electrons. Each orbital can only hold a maximum of 2 electrons. Each orbital can hold 2 electrons. And so I'm going to talk a little bit about what these orbitals look like here and how they behave. But the 1s orbitals, hydrogen and helium, right? You see over here, it would fit here. There's 2 spots there, so they can hold 2 electrons. The 1s orbital can hold 2 electrons. We move over to 2p, we've got 6 spots available to us in 2p. So there's 3 versions of the 2p orbital, 2px, 2py, 2pz. So each of those can hold 2 electrons. So total, the p block, or the p orbitals, can hold 6 electrons. Okay, we're going to get to that as we go, but I want you to see that vision a little bit ahead of time. Okay, so we're going to look at some electron configurations and see how they work. Okay, the electron configuration for hydrogen is 1s1. You don't have to write these down. I want you to look at your periodic table and see how these things match. Okay, the electron configuration for hydrogen is 1s1. Okay, so let's talk about what these things mean. 1s1. Oh my, okay, my having problems. Hydrogen is 1s1. So what do you think this big 1 stands for? Not quite how many electrons, but it stands for the row on the periodic table, or the energy level. Okay, so this is energy level. The S tells us that it's in that orbital shape, right? It's in an S orbital. And then the 1 here tells us that hydrogen has 1 electron found in this orbital. Hydrogen has how many electrons total? Only 1. So when you're checking your electron configurations, you can add up the number of these electrons and make sure it matches your atom. Okay, so let's look down, let's skip it down to a little bit bigger one here. If I look at boron, its electron configuration, 1s2, 2s2, 2p1. That's the electron configuration given for boron. So let's follow along on the periodic table. To get to boron, it's in what block? It's in the 2p block. And it's the first element in that block. So to get to that point, we had to fill our 1s orbitals, right? And we said 2 electrons can fit in an s orbital. Then we moved down to the 2s orbitals. 2 electrons can go in there. And then we move to the 2p orbitals. Boron is the first element in that block on the periodic table, so only 1 of its electron is in a p orbital. So the way you check that is we say, okay, boron's atomic number is 5. 2 plus 2 plus 1 equals 5 electrons total. Do you see on your pathway how we followed that along too? We went 1s, then 2s, then 2p. Okay, how are we feeling about that? Pretty good so far?